want to start by thanking the organizers for this great meeting. So many people working on these topics. It's really interesting to see you, and I would say that it's even interesting to see people at all after 2 years. So I'm really happy. Okay, so what I would like to present today is a set of works on the dynamics of asexual populations. So we restrict to asexual populations because we are able to derive some explicit propagation speeds for these. And it gives also a framework maybe to try to tackle sexual populations later on. So this is actually based on 2 works. The first one that was done with, that is currently done with Mathieu Alfaro and Ophélie Ronce. Mathieu Alfaro is in Rouen now. I should update that. And Ophélie is in Montpellier. And then there's a second work that was done by Julie Tournière during her PhD with advisors Pascal Maillard and myself. Okay, so we all know that climate change is going on. So there's a global rise of temperatures. So the climate change has a lot of consequences, some that are a bit difficult to foresee. For instance, the impact of climate change on precipitations is a bit difficult to predict. But the influence on temperatures globally is quite clear. There is a linear trend that is continuing. And so we can try to work on that and to see what could be the consequences of that for species. And lots of biologists are interested in that, obviously. So this is a kind of work that has been done has been done a long time ago, but I think it's representative of what can be said in biology. You have on the left the current range, or the range in 2003 of the beech tree that is present in the gray area on the left. So it's an emblematic tree of European forests. And then the authors have considered, tried to find a correlation between the presence, absence of these species and environmental conditions such as temperature, precipitation, type of soil, etc. And then they have tried to see in the future where these conditions for presence or absence of the population will be met. And you get on the right-hand side in 2080 that the population with this certain meteorological scenario, the species will disappear in the dark area and could potentially live in the light gray area. Okay, so this is correlation between survival and environmental condition, and there is in these studies there is no description of the dynamics of the population. Okay, and yeah, so we would like to go a little bit further than this along 2 axes. The first one is maybe try to see if it's possible to relate that to the life cycle of individuals with a bit more ecology in these discussions. And the second one is to add adaptation, because here there's when we do the correlation of local conditions and the presence or absence, we assume that all the individuals in the species are the same, and we know that this is not the truth. This is not very realistic. So I have an example here of a little flower, Capsella bursa pastoris, that lives a bit everywhere around the globe. And if we pick some seeds from these flowers in different locations here in California, and we grow them in a single garden, we see that the seeds produce actually very different individuals. The ones that come from snowy forests tend to flower late in the season, probably to avoid frost and over an extended period of time, while the one coming from much warmer areas close to the desert tend to bloom early and during a short time to avoid overheating. So this represents the fact that when you consider a species, there is a spatial structure, but there is also a phenotypic structure associated to this species. And when we want to understand the dynamics of this species, we need to take into account the dynamics along those 2 structures. This was an example with little flowers, but actually here I have represented different types of trees, and we have similar trends, often with an interpretation of this local adaptation that is much more difficult to do. So this is a model we'll consider. So as I said, it's asexual for simplicity. So when we have one parent, the parent will give birth to an offspring with the same trait as the parents, plus some little mutations. Okay, so there is no averaging going on like we would have for sexual populations. And we'll take the simplest model we can. So there's a spatial variable x. So we have a dispersion in x. This is this first Laplacian. Then we model mutations through another Laplacian in y. That's why we have the second Laplacian here. And then on the right-hand side, we have the ecological dynamics. So R, which is the growth rate, it depends on time t, position x, and trait y, and a competition term minus integral of n, which says that all the individuals present in a certain location compete together. Okay, even if you have different traits, you will compete for the same resources typically. And this is a growth rate, so we multiply it by n. We'll specify a bit more this R. Typically, we'll consider a R that is like we have R of x minus ct and y, and it will be given by 1 minus the square distance between y, my trait, and an optimal phenotypic trait that is b of x minus ct. Okay, so if t is set to 0, we see that the optimal trait is just a line, right? That this optimal phenotypic line, so it's this red line that I have represented here. So the growth rate is just 1 minus the distance to this thing. With time, this optimal phenotypic trait shifts to the right, okay, at a constant speed that is forced by the climate change. Okay, so there's a constant speed c that is given here, right, that shifts the environmental conditions towards the right. And if we do so, we are able to show that there is a critical speed. This is a c star star that I represent here. That is explicit. Lambda infinity is a principal eigenvalue, and in the case where with the finesse I have prescribed, it can be explicitly computed. And the result is if the climate change speed is slower than this c star star, the population survives. If it is bigger, it gets extinct. And so that's the first part, let's say. And if the population survives, it then automatically propagates at speeds that are also explicit. And the speeds are given in two sets. There's omega plus, the propagation towards, in the direction of the climate change, and omega x minus, the propagation in the other direction. Okay, and so it's given by those two formula. So here is a representation of that. The original situation is this one. We have here the optimal phenotypic trait at t equals 0 in a blue line, and the population is present around it. And as time goes by, the climate change shifts the optimal trait to the right, like this, and the population, in this case, survives and follows the optimal phenotypic trait. It cannot go too far from it, otherwise the growth rate is 0. And I will show a movie to see how it works. Right? We see that we start with initially with a population that is present in a little part here, and this optimal phenotypic trait is shifted to the right, and the population follows like this. And we see here we recognize two speeds. The speeds on the right, so that would be omega x plus, how fast this goes in this direction, and omega x minus, which would be the other side. Okay. Now, we can recognize several situations that make sense biologically. We have 4 situations in particular here. The first one is a very favorable situation where the population propagates in all directions. It propagates towards the south, let's say, and towards the north. Okay, so it's very favorable. We could have slightly less favorable situations here. Here, the population succeeds to stay put, so it succeeds to maintain its warmest edge, right? It adapts to the heat, but it fails to keep its niche. Okay, here we see that the traits y equals 0 were present initially and they disappear. Okay, so you fail to keep the niche that you had originally. You can have the reverse situation where the population succeeds to keep its niche. Here we see that y equals 0 is still present in the population, but you lose your warmer edge here. Okay, so you disappear locally. And you can have, of course, a combination of those two bad things where you neither keep your niche or your southern edge. Okay? So these are quite different situations, and we can take advantage of these explicit propagation speeds that are available for the full model with all the coefficients, right? So biological relevant coefficients like sigma, which is a dispersion rate, mu, the mutation rate, etc. And if we do so, we are able to investigate the role of the different coefficients. So this would be the case for mu equals 1. I haven't specified the other coefficients. We would have those 4 scenarios that are described before. If sigma is intermediate and c is small, the situation is very good. You keep both your niche and your southern edge. If you increase a little bit the c, depending on your sigma, you can either lose your southern edge or lose your niche. Then here you lose everything for C except the survival. And if you go a bit beyond, you end up in the gray area, and then the population gets extinct.
Sorry, excuse me.
Yeah.
Can you remind what is sigma?
Oh, sorry. So sigma was the dispersion rate. I will focus here on two things, on the dispersion rate sigma and the climate change speed C.
Thank you.
Yeah, sorry. Okay, so C is the climate change speed and sigma is the dispersion rate. And so we see that all those scenarios that we discussed before are possible. And if we change the other coefficients that are not included in this graph, this image typically change. So when we go from mu equals 1 to mu equals 0.3, we see that you can have significant changes with the importance of the different zones that can change widely. Okay. So since we have explicit things, we can go a bit further. We can try to analyze the coefficients more precisely, the impact of the coefficients. So here's sigma. So we see that if we have a sigma that is intermediate, we have here the speeds of the northern edge of the population and of the southern edge. And we see that there are optimal dispersion rates that are intermediate. If you disperse too much, it's not very good. Right? You will go too much into areas that are bad for you. And if you disperse too little, you will not be able to follow the climate. So it's also bad for you. Okay, so you have intermediate dispersion rates. And this optimal dispersion rate are not necessarily the same if you look at the warmer edge of the population or the southern edge. Or here on the right is the speed, but for the phenotypic trait. Right, in the phenotypic variable. So these things are different. But we can still draw some interesting parallels to simpler models. So in this model by Henri, Odo Dickman, Nageler-Kay, and Zegeling, they consider a model without a trait structure. And there they noticed already that you could have this intermediate optimal dispersion rate for that model without evolution. So we can see that here, that it's coherent. We can also consider things that are accessible because we have these speeds, and this is possible only because we have this adaptation. And we see, for instance, for this climate change speed, that if we look at the northern edge, actually, the propagation speed of the population is non-monotonic. When you increase the climate change, the population will move faster towards the coldest part, right? But there will be a maximum to that. After a certain climate change speed, actually the speed, the tendency of the population to move towards the cold places will slow down, okay? So this is what I wanted to present for the 1D thing, and we can try to go a bit further into the two-dimensional situations to try to get closer to the other approaches that we have seen. So what changes in 2D? Well, you have more directions that appear. So the idea will be to recycle what we have done in 1D. And there's a slight difficulty, which is that we have two directions. The first direction that we have is this red arrow here. It describes the gradient of the optimal phenotypic trait. Okay, the optimal phenotypic trait depends, for instance, if we assume that it's warmer in the north, it depends on the latitude. Okay, so this gives you one direction. It's towards the colder places. And then we have a second direction, which describes the perpendicular to the edge of the range of the population. If those two align, you are back to the 1D situation, but in general, they do not need to be aligned. Okay, so you have this angle theta that appear. It's not too bad because actually we are able to see that the impact of the theta can be treated and extend the formula that we had before. We just have some sine theta and cos theta that appear here and there. And an interesting feature is that this can change sign. We have this cos theta, okay? So this can change sign. So the speed here, the blue arrow, can either go to the right or to the left. Okay, you can continuously change from a situation where the population extends in this direction or retracts. So from this you can investigate the dynamics of shapes, and in particular find that there is a special situation where the population is distributed like an ellipse. And this is an exact solution. Okay, it's a bit similar to what you would have with Fisher KPP, where you have that the population propagates like a disk. Okay, a disk that would increase at constant speed. Here you have something similar, but it's an ellipse. Okay, so this ellipse initially is a blue line. So it's a certain well-chosen ellipse with a certain ratio between the big and large radius. And as time goes by, this ellipse increases in size at a certain speed and moves northwards. So you have this special solution, and we believe that actually any range with bounded shape will converge asymptotically to this ellipse. Okay, so we haven't proven that, but we believe that it is true. And this raises two questions from the biological side, because actually it doesn't really look like what we see here. This is the current range of the beech tree population, and we see that it's not an ellipse. So how can we understand that? Well, there could be two ideas of the limits of our model. The first one could be that actually we consider asexual population. The beech tree, like many populations, are sexual, so this could be a difference. And another difference could be that we considered an environment that is too simple, that is like linear in space. We have just an optimal trait that changes linearly in space, and maybe this is not enough. So we will try to consider the second problem here in this talk. So it would be to consider heterogeneous situations. So this here is a representation of the world climate data for temperatures in Europe. And we would like to analyze the dynamics of a species that would be the black line here. How can we do that? Well, we can get some ideas from a work that was done by Freiglin in 1985. And he considered here a set of reaction diffusion equations in 1D. So there is no more phenotypic trait in this, this part of the talk. We have only this space variable x. And we have a heterogeneity that is R of x. This R of x is multiplied by a growth rate that is f of n tilde. And this growth rate can have two structures, either a monostable structure, so f of n is 1 minus n. This is reminiscent of the Fisher-KPP equation. Okay, if R is constant, you get exactly the Fisher-KPP equation. Or you can have a bistable case where the growth rate is negative when the population size is too small and becomes positive after a size of theta is reached. So these are two different situations. And you can, to study the dynamics of these populations when the time is large, what was proposed by Freiglin was to introduce a small parameter epsilon and to consider that those heterogeneities happen at a large scale. Okay, so we're not thinking of very fine details such as, I don't know, the alternance of roads and fields, but large-scale features such as mountains or deserts and stuff like that. So this would be relevant, I think, for the scale of the continental scales that we had before with the map of Europe and the temperatures. So to study this, he introduces this small parameter that specifies that R is heterogeneous on a large scale, and then he performs a hyperbolic scaling on n, right, to keep the speeds constant. And when you do that, you inject two epsilon parameters, one in front of the Laplacian here, and one over epsilon in front of the reaction term. Okay, and then what you can do is try to see how the propagation of the population behaves when epsilon becomes very small. So you consider an initial situation where the population is present. Okay, the population is present on the half space only, right? You have here x equals 0, and you let the time go by. And so this one will propagate here, and you follow the location of this one, you call it x of t. And you wonder, can you describe the time derivative of x of t? And so what you have is here the heterogeneity is prescribed by this R of x. Okay, we have a R of x here. And the idea is this, because of this epsilon, the transition from a high population to 0 is very sharp here. So on this scale, actually the R is not moving very much. So the R is almost constant. And because it's almost constant, you can consider, well, actually, x of t will not see the spatial heterogeneity of the R. Okay, so if it doesn't, then the speed of x should be equal to the speed when R is constant. Okay, so 2 square root of R of x in the case of Fisher-KPP, or in general, a certain formula, CR, right, that we don't specify, okay? And the question is, does this give you the right speed or not? And so what Freiglin said is, it does give you the right speed when you are in the bistable case. He called this the Huygens principle in reference to some discussions in that had to do with light. You know, either you see it as a particle or a wave, right? So in this case, Huygens principle, the speed of this heterogeneous case is given by the localization of the speed. But in the case of the monostable situation, this is no longer the case. And actually, if you consider only the instantaneous speed, you shoot too close. I mean, the population is typically faster than that. Okay, and the typical example of that is a situation where this R would become 0 at some point, right? and after a while it becomes big again. So what you will have is the population will propagate up to the edge of R positive. It will stay there for a while, but every now and then you will have a few individuals that will succeed to reach this good area. And so little by little, this one will grow again. Okay, and then they will have crossed this area where R is equal to 0. So it's not true that R equal to 0 blocks the population. So this is well known, and this is studied with Hamilton-Jacobi equations, or another term is the one used by Freidling, which is a geometric optics approximation. And this plays a big role in many situations, and we have seen it with the talk of Adrian and Sepide and other people. And it really plays an important role for evolutionary biology as well. But here we would like to understand, to have the second one, right? Because the second one has an advantage of simplicity. Here we have an explicit speed, and we don't need to simulate, for instance, the whole PDA anymore. So what can we do? Well, we can do something that was already proposed by several authors, Sepide, Miraimi, Guibal, Penaud-Apertam, Souganidis on one side, and Champagnat and Jabin on another side, which was to introduce a small perturbation of a monostable case to add a little bistability. Okay, so if we represent this F, or I represent f of n times n. The monostable case is this one, right? And I can notice that if I introduce just a little bistability here, somehow, I jump from the first case to the second one. So I have directly, no matter how small this one is, I have the Huygens principle. So I can do that, and I shift from the geometric optics approximation case to the Huygens principle. And here what we propose is something along the same line, but instead of introducing this little bistability, what we will do is we will go back to the stochastic individual-based model underlying the FKPP model. So we introduce a parameter n, that is the typical size of the population, and we consider a population that is contains a finite number of individuals on a grid, and they move around with random walks, and they branch with a rate r that depends on epsilon t and epsilon x, and there's competition among them with a rate 1 over n to recover the typical population size, big N. Okay, so we have now two parameters, the big N and the 1 over epsilon. And what we have as a result is this one. If you first consider epsilon goes to 0, so first you consider large-scale heterogeneities, and then consider large population, you recover the Huygens principle, that is, the dynamics of the rightmost particle, the particle that is here, is given by the explicit speed from the Fisher-KPP equation. Okay. And so, and if you invert those two limits, you are back to the Hamilton-Jacobi case. So to prove that, I will not describe the whole proof, but an interesting idea is that we try to couple some very classical arguments from nonlinear PDEs and traveling waves analysis with stochastic processes tools. So there are two things that are a bit similar. We have the comparison principle for parabolic equations that play a very important role when you want to build a traveling wave and consider spreading speed in particular. The comparison principle tells you that if you have n solution of this one with a competition term and m a solution of the same one without this competition term, and if initially n is lower than m, it will stay so for all times. Okay, so this is, I will draw that. So you have initially one solution that is underneath and one that is above. And what will happen with time is that this one will continue to live its life, and the one underneath will stay underneath. Okay, so the order between those two will be constant. For stochastic processes, it's no longer the case if you try to do it directly, right? Because if you have a stochastic initial condition for one that is like this, and the stochastic initial condition that is this one for the other one, and you let the stochastic simulation run, well, typically you can have this one that suddenly produces a lot of children, and the top one that does the opposite. A lot of individuals die suddenly, and then you have this ordering that is not true anymore. Okay, so you cannot do it directly, but you can actually build something similar to the comparison principle through a coupling argument. So what you do is that you build the stochastic processes in a certain way. So you will first build the solution of the yellow one. So you consider that in the yellow one, for instance, you have some individuals that are born like that. Okay, the yellow one, in the yellow process, you have no competition. Okay, and then you want to build the one for the red. So the red, there is competition. So what you will do is you will just pick the one that you have constructed with the yellow, right? Considering that when you do that, you simulate the dispersion and the branching, but then you add the competition, and the competition can only kill some people. So for instance, you will say, well, when I go to the red one, I keep this one, I keep this one, oh, the colors are not very good, and for instance, this one disappears. Okay? And so I have, at that moment, constructed two things at the same time, the yellow process and the red process. And through these constructions, they'll be ordered. And this will be kept in time. Okay? So this allows you to extend this comparison principle idea. Another thing that you want to extend are fundamental solutions, or more broadly, exact solutions from the linearized problem. So in the case of PDEs, what you have are typically these Gaussian distributions, okay, that are solutions of the linear PDEs. And for stochastic processes, what you have are branching random walks that are situations where you start from a single individual, and this individual can disperse and branch, etc. And this is a bit less explicit, than the Gaussian distribution, but it's also very well understood. Okay. So how do we compare these two particular solutions, so Gaussian distribution for the linear PDE and the branching random walks? Well, there are some similarities. If we take the expectancy of the branching random walk, you have something that is similar to the Gaussian distribution. So there are little differences because we had to include a spatial discretization that I don't want to discuss here. But basically, it's almost the same. And also, the propagation speed of this expectancy is linear in time, a bit the same. Okay? But there is a big difference. The difference is when you consider a branching random walk, it starts with one individual, and this individual produces a finite number of offsprings. So let's consider here the time t, and the correlation x. So we start with one individual here. It gives rise to a certain number of offspring, but then we can define here the rightmost individual of this random branching walk that we call mt, and there is no one on the right of mt. Okay? This is very different from the PD, where you have people everywhere as soon as t is bigger than 0. And this can be understood through this little calculation here. We consider the probability that the rightmost particle is bigger than IC, so the time times a certain speed, plus A. We say that this probability is equal to the probability that this is bigger than 0. And if this is bigger than 0, actually it's bigger than 1, because it did put some 1s here. And so this is less than this expectancy of the same quantity, okay? Now, when we do so, we can use this many-to-one lemma that we have seen this morning already to estimate that through a certain growth rate of the population size, this 1 plus r delta t to the e, times the probability that one single individual that doesn't branch anymore is on the right of IC plus A. And this is a simple random walk, and we can estimate the probability that it satisfies that and have an explicit control of this probability. And this is coherent with the speeds of Fisher KPP that we have on the PD side. Okay, so with that, we are able to consider an upper bound for our process. So I will describe it here. So we consider an initial population that is present until a rightmost particle xi, okay? And then what we do is we consider that since there's no one on the right here, we can bound this by a finite number of individuals in each site like this, okay? And for each of these individuals, we just run a random branch-home walk like this, okay? And then we'll consider at a later time is I delta t plus 1 over epsilon, okay, something quite large. And we'll consider the position of the rightmost particle of all the random branching walks that originate from the particles here that we had originally. And if we do so, we're able to say that actually with high probability, with probability 1 minus exponential minus alpha over epsilon, the rightmost particle at the larger time is lower than the rightmost particle originally, plus something where we recover the deterministic speed times this interval of time, etc. Okay, and this here actually looks very much like a Euler scheme for a simple ODE, which is this one that we had before. And like this, we can show that the rightmost particle propagates at most as fast as this ODE that we had here. Okay. For the lower bound, it's a little bit more complicated. Why? So let me just describe it here. We have this initial population here. And this time, we want to bound it from below. So we actually neglect all the individuals, but the rightmost one. Okay, and we'll consider that there is only this one present initially. And so we run a branching random walk for this one. We'll consider its rightmost particle after a certain time. And then we want to say that this one is under the original model. But to do that, we have to be careful because this time there's competition that we did neglect for that. Okay, so we have to run this random branching walk, but not for too long, because otherwise the size of these individuals can go beyond the acceptable size to neglect the competition. So actually, we need to consider shorter times that are not like 1 over epsilon, but more like log of big N. Okay, so much shorter times. And these go to infinity when n goes to infinity to 0. Okay, so we have a lot more intervals like that. And so instead of having a finite number of individuals like that, we have an infinite number of intervals. And so we have to use a central limit theorem idea that is done with the Doob inequality. And we are able to show that the population propagates at least as fast as the ODs that we had before. Okay, so I don't know. Oh, sorry. Okay, so you can apply that. So along 2 lines. The first one is to apply it to theoretical things. So here we have an example of a wildlife protection area. So we have increased the quality of the environment on a certain interval, and we try to see what is the effect of that. And we show that it can actually save the population. So we have a population here, and here we have with this wildlife refuge, and we see that we are succeeding to keep the population here on the left, and actually because it survives here and on something that is going towards the north, actually the population survives everywhere in between. Okay, so this could be an interesting situation. Another one is a mountain. So if you consider mountains, you can see that it's easy to climb the mountain because it gets colder when you climb the mountain, but it's difficult to go down the mountain because you have to face climate change and the elevation of temperature that you have when you go down a mountain at the same time. Okay, and so for this OD framework is very convenient to use. The last thing that we can try to do is to use that for large-scale simulations. So here there are lots of discussions that would be necessary. So this is very preliminary work. And there are lots of discussions that would be necessary to have with biologists, specialists of the field, to see what is the validity of this kind of simulations, and if this means anything at all from a biological point of view. Anyway, we can use, because we have this explicit speed, we can use fast matching algorithms that are perfect to do those fast simulations. So we used here an algorithm made by Jean-Marie Mirbeau and his collaborator for the Fisher-KPP equation, and we can try to extend it for the situation where we have also a structure in trait, and there are some extra difficulties that appear. Here's an example. You have here a speed that can become negative, and so this is not included in a fast matching algorithm a priori. So we have to find some new ways to do it. And there are also some anisotropy things that we don't know how to solve yet. But it could be interesting to try to do that in the future. Okay, thank you.
Okay, thank you, Gaël. So is there any question for our speaker?
How much of the stuff that you presented with the probabilistic models can you handle with just analysis PD methods and Hamilton-Jacobi? So you brought up like the Souvenidis, Takis, and Benoit papers and whatnot.
Yeah.
Yeah.
So if instead of adding a finite population size, you add a little bistability like that, actually it's quite straightforward from the Friedlin paper. So he didn't introduce the fact that this could go to 0, but it's almost included. You don't have to go through the more complicated things that have been introduced for this section mutation paper that I mentioned. So, but what we wanted here is really to justify this by going back to the individual-based model. So the difficulty here is that you introduce something that is difficult to justify. Right?
So any question? So in your simulation, so is it so did you simulate it as a free boundary problem? So using the formula that you have with the normal velocity given by 2 square root of
yeah, so I used this formula, but I just fed it. I mean, it was done by master students, right? That I mentioned. Sorry, here, Fanny Dupont and Ferdinand Campos. So they used this algorithm that was made elsewhere, and it's fast matching. So you try to compute how much time you will need to go to any point in space. So that's the idea. So it's not really free boundary. It's more
like the shortest path, right?
Yes.
So you also mentioned you have a simulation with also trait structured population.
No, we haven't done everything. So it adds, yes, some difficulties. So anisotropy. So the speed that you have can depend on the direction of the interface. So that's not included typically in fast matching algorithm. And the speeds that can change sign. So we did try here to have the negative speed. So this works now. But for the anisotropy, we haven't done it yet. So I don't know how to do that. Yes.
When you talked about the mountains, can you quantify, let's say, how steep the mountain has to be in order to block the propagation?
Yes. So the mountain is an interesting thing because for the refuge we could use fully rigorous things on the PDE, but for this one we have to rely on that because we say the population doesn't succeed to go down the mountain, but we know that a little bit further it will actually succeed to survive. So we really need this argument to say that it's blocked. We just need to have this omega plus x, and we have a formula that is equal to 0 in the largest slope of the mountain.